Hello YouTube, and welcome to this introductory video on discrete probability distributions and what they are and how we interpret them and construct them and why we have them. Okay, so since this is an introductory video, we're just going to kind of go ahead and explore this idea of what a probability distribution is in the first place before we start to create them. So if you're looking for practice, you can skip to the end of the video, but we talk about what are probability distributions, okay? And think about this word probability, it is a likelihood. There are a lot of times in life where we'd like to maybe predict something that will happen in the future based upon events that have already either taken place or theoretically that would exist. So for example, flipping a heads or a tails, we could say, how likely is each to occur? That would be a theoretical likelihood that it occurs. Or let's say we work in, say, the insurance business, and I want to know how many claims are going to be filed on a given day. I can actually go back and look at the data for how many claims are filed on a daily basis. And based upon that information, say what percentage of the time we have, say, 0 claims, 1 claim, 2 claim, or however many claims. But essentially, when we talk about probability distributions, it is looking at how likely it is that certain events might occur in the future based upon either their data in the past or theoretical likelihoods of them happening in the first place, okay? When we talk about probability distributions, it's important to start with this idea of what we call a random variable. Recall that a variable is just something that's changing, okay? So these are things that we could collect data on. So this could be like height, weight, mass, anything that's a variable, anything we can collect data on, okay? But we say a random variable is specific. It is a variable whose values are determined by chance. So we could say, let's let our variable represent the number of, say, heads that we flip when we flip a coin 10 times. Or we'll let X, which is our variable, represent the number of people that show up to a speaking engagement if we're a speaker and we keep track of how many people show up. But we could say those things are random. They occur by chance. We don't know what's going to happen in the outcome. But we do pick a variable to represent that value, okay? So a random variable, we use letters to represent these things, and they often represent values of things that could necessarily happen, okay? So we do want to distinguish between a discrete random variable and continuous random variables. Recall from the past that anything that is discrete is something that must be counted, okay? It is a counted variable. So these are things like number of vehicles, we say number of vehicles, number of people, we say number of books. These are all instances of things that I collect data for that I would have to count, whereas continuous random variables, these are things that must be measured, okay? So things that must be measured are continuous. We say these are things that we could refer to as maybe like time. Time is something that I measure. Or we could say volume or mass, okay? So when we talk about variable types, I want you to know this. In the next set of videos that we're doing here, we're going to only be discussing discrete random variables, or variables that we can collect data for in which the data type is something that we have to count, okay? But we say a random variable is any variable whose values are determined by chance, and we're going to be focusing on discrete random variables in this video here, okay? So when we talk about a probability distribution and what it is, why we use them, we use these things to make predictions on what might occur in an experiment based upon what we've seen in the past, okay? So we're just going to jump right into this and talk about how would you construct a probability distribution, what do they look like? So we're going to consider a thought experiment. We say, considering an experiment in which we flip 3 fair coins. The only reason I mention these are fair is that one side's head, the other one is tail. It's not trick coins, okay? But we're going to flip 3 fair coins. What I want to know is this: how likely is it that I get a certain number of, say, heads, okay? So the first thing we're going to do is this. We're going to define our variable here. We say, let's let X be the number of heads flipped, okay? Maybe what I want to know is this: how likely is it that I get a given number of heads in this experiment? So in order to explore this a little bit, what we're going to do is we're going to construct the sample space for the experiment. That is, write out all possibilities for these three flips, these 3 coins. So for instance, if I were to flip 3 coins, I suppose we could get a heads, another heads, and another heads. We could get a tails, tails, tails. I mean, these are all possibilities here. We could get like a heads, tails. I suppose also then that a tails, tails, heads would be a possibility. How about heads, tails, heads, tails, heads, tails? But also we've got this tails, heads, 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 tails, tails. And these would be the 8 different possibilities for this experiment, okay? But what I'd like to do is this. I want to analyze, how likely is it that X is 1, 2, 3, or 0 when it comes to X being, the representative of the number of heads that we get here. So a probability distribution is constructed thusly. we always start by putting our variable in one of our rows of this probability distribution, one of the rows, okay? And you notice that I've already got this table set up here, but I say x, we're going to let x represent the number of heads that happened on each of these outcomes of this experiment up top. So we either could have gotten no heads when we flip 3 coins, that would be this case here. We could have gotten 1 head, 2 heads, or 3 heads. But what I want to know is how likely is it that I'm going to get, say, no heads, or say all heads, or something to that effect. In order to answer this, what we're going to do is we're going to create a second row, and this second row right here is always the probability that this individual event actually occurs. So you'll notice here that I write x on top, but I also write p of x on the bottom. And what this is really saying is this is how likely it is that we're going to get this many things. So for instance, I say, well, how likely is it in the experiment we just considered right here that we would get no heads on the coins? We say, well, out of all 8 of these possibilities, because there were 8, how many of them consisted of no heads? And there would be this one right here where we had all tails. So we say the likelihood of this is a 1 in 8 chance. Okay. Furthermore, we said, well, how many of these had like only 1 head in them? Okay, so we'd say 1 head. 1 head. We had this instance here, so we had 1 there. We had also 1 head in those right there, and we also had 1 head in those right there. So I suppose the likelihood that you're going to get 1 head when you flip 3 coins is a 3 out of 8 chance. Same thing with 2 heads. We say how many of these had 2 heads on them? So we said tails, heads, 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 tails, heads, and heads, heads, tails. So this was also a 3 out of 8 possibility that that occurs. And then how many of these had 3 heads in the outcome? And we say it was only 1 of them right here. Okay. So one thing I want to notice about this, or a few things I'd like to kind of start out by noticing here. When I look at this, what I can tell you is how likely it is that when you flip 3 coins that you're going to get a given number of heads on the coin. Okay. Also this, we say that there were only 4 possibilities. You could have gotten no heads, 1 head, 2 heads, or 3 heads. And what I want you to notice is this: if we were to actually add up all of these probabilities in the basement here, 1/8 plus 3/8 plus 3/8 plus 1/8, we would get the sum of all the probabilities coming out to be exactly 1. And the reason why is because our probabilities should add up to 100% of the total number of outcomes. Okay. Furthermore, what are the things I want to say about this? We can convert these to decimals if we'd like to. We've got a 12.5% chance here. We've got a 0.375 here, 0.375. This would also be 0.375. And this one back here would be 0.125. And if we summed all these, we can see also that we get 100% of the possibilities here. But this is what we refer to when we talk about a probability distribution. Pretty straightforward. You say, let's let x represent the things that can happen, and let's let p of x represent the likelihood that each of those events actually occurs. Okay. So when I referred to this video as something where we're only going to be discussing discrete random variables, this is important that we recognize that what we just created here is referred to as what we call a discrete probability distribution. It shows how likely it is each thing that can happen will actually occur. But we refer to this as discrete because it consists of values of a random variable that can assume and the corresponding probabilities of the values. Okay. So the probabilities are determined theoretically or by observation. This just means that if we're flipping a coin, it's in theory, you know, a 50-50 or something like that, or by observation, which means we could collect data on it, and based upon what we've seen in the data, we can make predictions about how likely it is that each of these events actually happens. Okay. So we're going to do this again here on example 2. We'll be done with this video, but we say let's construct a probability distribution for rolling a single die. And what I want to do is I want to start by defining what we're going to let our variable equal. So let's let x equal the number of dots on the die after rolling. So basically what number you roll. Okay. When we create this then what we need to start with is this. What are all the likely possible outcomes, the sample space of this experiment here? Because what we're going to do is we're going to create this probability distribution in which we put x, which is our variable up here, and the probability of those x values down here. So when we say x represents the number of dots on a die after rolling it, we say, well, how many dots could be showing on the die? And so, you know, thinking about this, we could say, well, we could roll a 1, we could roll a 2, we could roll a 3, a 4, a 5, and a 6. Okay. So what we're going to do now is we're just going to go through individually each one of these and say, well, how likely is it that each of these things actually happens? Because on a die, you know, recall that each number only shows up once here. So we say 3, 4, 5, so we'll call it 6. So we say, how likely is it that we actually roll a 1 on a die? And of course, we know this is a 1 out of 6 chance. How about a 2? How likely is it we roll a 2? Well, we got, you know, a 1 out of 6 chance there, so we have 1 out of 6. As a matter of fact, if you're thinking about this, all of these In this experiment, it will be 1 out of 6. So a few things we could say about this. First of all, if we were to add up all of these probabilities down here, that is, sum up all of the probabilities or all the likelihoods here, we always get 1 or 100%. Okay, so it's all the possible outcomes. The other thing I want to mention about these is they're all the same. Okay, you notice that these are all the same because what we were using was a fair die. That is, everything that's on the die is just as likely to happen as anything else. Okay, but this would be our discrete probability distribution for the experiment of rolling a die. We'll get into more complex experiments in the next video.